Hello, everyone, and welcome to our live session for today, August 29th, 2025. We are excited to be here with you. My name is Matthew. I am one of the course instructors. I do a lot of the behind the scenes stuff. And in just a moment, I will let Professor Impey introduce himself. I'm just going to go over the sort of the process for the live sessions. And for those of you who are new, welcome. The way this works is we have you post your questions in the chat. I will grab questions from there and ask Professor Impey. Please ask your questions only once. We do see all of the questions. I generally try to go in order that they are asked and received, but I do sometimes jump around to give people, a variety of people, an opportunity to have their questions answered and to cover a variety of topics. Please remember that this is a beginner level, so we try to keep this at an introductory level. So if you have super high level mathematical or physics questions, you'll have to look for those answers somewhere else. We also make sure you hit the thumbs up on this video and subscribe to our YouTube channel. Hit that bell icon so that you hear about upcoming live sessions. Chris, you usually have a topic for us that you like to introduce and just kind of potentially guide some questions and discussion. So if you have one of those, we'll get started. If not, then we can grab questions from our participants.
Okay, sure. I was going to give a little update on large telescopes. I've been away for a few weeks on a cruise, North Atlantic cruise. And having been on cruises where I'm the working astronomer, like Viking resident astronomer, giving a lot of lectures and star parties and so on, it was refreshing to actually be a participant and just occasionally participating in astronomy. And the guru and maestro of the outreach on this cruise was Tom Vassos, an astronomer out of University of Toronto. So it was a lot of fun to just sit in the audience and watch his talks instead of having to give talks of my own. So that was a very pleasant last 3 weeks. On the news front, I'll just give a brief update on the state of the impending large telescopes. As people are probably aware, astronomers are heading towards a new generation of super large telescopes. There are three major projects in play, and they've each got different timelines. They're each different sizes, each have different technologies involved in their mirror making and design. And their progress has been affected by external circumstances. In some cases, building a big telescope is not simply a matter of solving technical problems or even just of raising the money. So in order in which these telescopes are likely to see first light, the European project, the extremely large telescope, 39 meters, is in the catbird seat, if you like. It has the fast track to first light, probably by the end of the decade. 2029 is a good guess. Because this is a project of the European Southern Observatory, where the member nations are part of a treaty organization and the budgets are designated by treaties between the governments, which means they're pretty stable within the EU system. And so this project is essentially fully funded. I mean, they have technical hurdles and they have to progress at a particular rate. Their telescope is destined for Chile, where the other European Southern Observatory sites are at La Silla. And it's a huge telescope, and it's going to be a prodigious improvement on the largest telescope available now by an order of magnitude in light gathering power. Likely second on the sky will be our telescope, the Giant Magellan Telescope, and that telescope has passed various technical hurdles. It passed its design review, its final design review through the National Science Foundation, which essentially says that it's ready for construction, that it's ready to be built. There are no road stops. However, that design review approval did not come with any money attached. So the problem for the GMT is it still has to raise some money, probably about $500 million on an eventual price tag of about $2 billion. There have been a few recent partners at it. That telescope is based on 7 8.4 meter mirrors built at our mirror lab at the University of Arizona. All of those have been cast, and they're in the various states of polishing and sending down to Chile, where the observatory site is at Las Campanas, so about 100 kilometers away from the European site. It's a very similar part of Chile, where the major observatories are. That's the second project, and again, it could get first light with 3 of the 7 mirrors, giving it the full angular resolution but less light gathering power, probably about 2030 or 2031, best guess. The third project has the most uncertain timeline, although it doesn't have any major technical issues. This is the TMT, the 30-meter telescope of Caltech and the University of California and other partners. And the roadblock here has been the construction on Mauna Kea. So that has always been the site for this telescope. It's site to many of the world's largest telescopes, but also of a vociferous opposition from native Hawaiians, either to new construction or just to continuing to build large objects on what they view as a sacred mountaintop. And there's been a sort of standoff in that situation, which has led to a pause on construction for several years, to the point where the Californians have had to visit other sites or think of other sites. Their likely relocation site would be La Palma in the Canary Islands, which is also site to a number of telescopes. La Palma is that high altitude site is not as high as Mauna Kea. It's not as dry. It's not quite as dark. It's slightly inferior in every aspect, but not dramatically so. It's a very good site. The Spanish government has tried to sweeten the pot with something like €500 million in incentives and price offsets if they choose to relocate from Hawaii, from the planned Hawaii to La Palma. And at the moment, the jury is out. Nobody knows how that's going to go. But all these uncertainties over the site selection mean that that would likely be the third of these large telescopes to go on the sky sometime in this 2032, 2033 timeframe.
Well, that is all very exciting and kind of nail-biting, I'm sure, for the community. So the first question is, so again, if you have questions about any of those telescopes or large telescopes in general, please post those in the chat. We'll start with some questions that have already been asked. The first question is from Crazy Lazy, who asks, I would like to know about the most promising method that will help us detect or might help us detect life on exoplanets in the coming decade.
Well, probably the most promising method, which is depending on technology that's still being developed and a NASA mission that is very much uncertain given NASA's funding envelope and budget uncertainty, is the terrestrial planet finder. It's a telescope, it's a project that hasn't had several name changes, but it's basically a very large space telescope specifically designed to inspect the atmospheres and isolate the light, reflected light from exoplanets, Earth-like exoplanets. And the secret ingredient of this telescope is a starshade. So the starshade is a free-floating device that is designed to perfectly account for the light from the central star and correct for it or blot it out so that it can be subtracted from an image. Because the surrounding light of a planet, or reflected light from an Earth-like planet around a sun-like star, is about 1 billion times fainter than the star. So the starshade is a crucial ingredient. So this free-floating starshade, free-flying, separate from the telescope, some kilometer or more ahead of the telescope, has to be positioned with exquisite accuracy. Now this can be done. NASA's done this kind of precision flying, if you like, before. But this is a pretty technically challenging mission. And that mission would allow us to inspect the atmospheres of more than a few, dozens of truly Earth-like exoplanets and inspect their atmospheres for the spectroscopic signs of life. And that's the most compelling experiment. Versions of this experiment can and will be done with the James Webb Space Telescope and large ground-based telescopes, including the 3 I was talking about earlier. But this future space mission is essentially the killer app for detecting life by looking at exoplanet atmospheres.
The next question is from one of our live participants, a remiss guide, asks, hello, Professor. My question is, if you have a Schwarzschild or stationary black hole and a Kerr or rotating black hole that collide with each other, what would happen to their singularities, a point and a ring? How does that combine? And I mean, and ultimately, like, would we be able to detect that with now our gravitational wave capabilities?
It's an interesting hypothesis. First of all, we imagine that in the role of normal astrophysical evolution, it's very unlikely to generate a stationary black hole because all the processes of stellar evolution and collapse involve objects that are rotating and have angular momentum. And so the black holes that result will have angular momentum and be rotating. But just imagining for a moment that you could have a stationary black hole to collide with a rotating black hole, then according to general relativity, as those objects merge and their masses combine, and of course there's a rich spectrum of gravitational waves emitted that can be predicted and simulated by theory quite well in anticipation of their detection by LIGO, then indeed the conservation of angular momentum would suggest that the combined black hole would have a ring-like singularity with a different radius. And I'm not sure how mathematically that radius relates to the initial radius. It probably depends on the relative mass of the two black holes. So that would be the prediction. The signature of such event would be very unique. And so when you saw a stationary black hole merging with a rotating black hole, it would easily stand out from all the black hole mergers that have been seen so far, which have the signatures of two rotating black holes combining.
Thank you. The next question is from Wendy, who sent an email. How is it possible to calculate the half-life of an isotope that is 1 million years long, or these extremely long periods? How do we figure out those half-lives?
Right. So when half-lives are very long, and some of the half-lives of radioactive elements like uranium and plutonium can be billions of years, then essentially we do it by the power of large numbers. So when you have a sample, and even a small sample of a radioactive element, assuming it's a pure sample, it's got trillions, many trillions and trillions of atoms. And so even if only a very small fraction of those atoms are decaying in the interval of your experiments, maybe weeks or months in the laboratory, it still amounts to a significant number. So it relies on the large numbers of atoms in a particular sample, where the small fraction that decay in a short time is still a substantial number, and the fact that atomic techniques allow us to isolate and count small inventories of atoms in a large sample. And so we can make the measurement fairly reliably. And the half-lives of these heavy elements that are extremely long are fairly well-determined numbers.
Thank you very much. The next question is from AKA the Best. Hello, Professor Impey. I want to ask if there are any books, shows, podcasts, or anything specific related to space that you recommend to improve my general knowledge about the universe.
Well, there's so many that actually it's impossible to give a list. I think your friend here is YouTube. So you can turn to YouTube, and there are channels that have astronomy content. And there are individual lectures on YouTube. In fact, YouTube is an incredible source of astronomy lectures on whatever subject. Just type in your keyword, exoplanets, black holes, galaxies, whatever you like, and you will find not just dozens, but hundreds of lectures. So as always with these things, look at the provenance of the lecture, because there's misinformation out there. There's pseudoscience out there. There's people, touting theories that are not quite legitimate about gravity and about cosmology. So you have to look at the source of the video. And that doesn't mean just the quality of the video. There's some very slick, high quality videos that are scientifically very thin. So you have to look at the credentials, essentially the provenance of the person who put the video together. What is their other work? What other work do they have online? What do their websites say they do? What's their affiliation? And if you take that little extra precaution in the sea of content that you'll find, I think you'll be looking at hundreds of hours of viewing enjoyment.
And then you've contributed to some podcasts before, I
Mhm.
think. So, like 365 Days of Astronomy is one that you've
Yeah. So there are
participated in
podcasts.
before.
Podcast is an interesting category because it's had rises and falls in popularity. The death of podcasting has been predicted several times and hasn't come to pass. But there are many podcasts out there, and 365 Days of Astronomy has been going for a couple of decades, actually. So it's really one of the longest lived ones. I think it started in the year of astronomy in 2009.
Yeah. And then the other one that I can mention is Astronomy Cast. I have a friend who works on that, and I think that's a good one. And then Star Talk Radio is always a good one with Neil deGrasse Tyson. I think that's would be fairly reliable. The next question from Lawrence K is um, if massive or supermassive black holes are colder than the cosmic microwave background, don't they absorb more heat and then they than they emit? So how do they evaporate? And what about smaller black holes?
Mm. So that's an interesting question. So yes, it is true that the temperature of the Hawking radiation from a massive black hole um, is substantially lower than the microwave background temperature of 2.7 Kelvin. In fact, it's very much lower. It's a tiny fraction of a Kelvin, of a single degree Kelvin. Um, so what does that imply? The black hole is still radiating. It just means that it's at some level endothermic because it's surrounded by a larger radiation bath. But that's not sufficient to stop the black hole from radiating because, again, remember, the black hole is sealed off from the rest of the universe. So the event horizon marks a boundary, an information boundary, information barrier between the black hole and the external universe where the background radiation is.
The next question is from an email. Christina sent an email concerning the Fermi paradox. Why would an intelligent civilization want to contact us? Might such civilizations regard us in the same way that we regard single-celled organisms as a form of life, but not yet as life in a more developed sense?
I certainly agree with the premise that behind the Fermi paradox or Fermi question, where are they, lies an assumption of the similarity in development of the two civilizations that are potentially talking to each other. If there's a sufficient mismatch in intelligence or technology or capability, then there's really no plausible prospect of communication. We can just look at the Earth for an example of our communication technology now versus when we were hunter-gatherers, for example. We had no technology at all, let alone the communication technology of other creatures on the Earth that may be intelligent, like orcas and sea lions, but that don't have technology or telescopes. So it is true that the assumption of commensurate capabilities weighs into the Fermi question. There's also the idea that you might not want to communicate. A very well-known trilogy of books, science fiction books called The Three-Body Problem, that are based on the dark forest hypothesis. The dark forest idea is the idea that in a universe where advanced civilizations may have extremely powerful capabilities to destroy other civilizations they don't like or they don't think need to be in the universe, then the best strategy is actually to stay quiet. And if this is a widespread phenomenon, then this could explain, of course, why the universe is not filled with the communications of civilizations. They're basically playing it safe and keeping quiet.
The next question is from Crazy Lazy, who's on with us live. If dark matter doesn't interact electromagnetically, how can we even hope to detect it directly? And what is the most promising method right now?
Almost all the methods for detecting dark matter, if we assume that it's a new type of fundamental particle, involve the mechanical properties of the dark matter, its collisional energy, essentially. So dark matter will be traveling at some significant speed through the through the air of an experimental situation, through the solar system, through the galaxy. Dark matter particles are all around us, and they outnumber normal particles by a factor of 5 or 6. So the experiments that are being built essentially have a very pure detector, which could be a solid or a liquid or a gas. And basically you're looking for collisions of the dark matter particle, which is massive, fairly massive, with atoms or electrons or molecules in the detector. And you're looking for that collision energy released either as heat energy or as sonic energy using a hydrophone, or occasionally it comes in directly out as electromagnetic energy. So in the absence of electromagnetic interaction, you look for essentially collisional energy from the dark matter particles. That's a very difficult thing to do. You need an extremely pure detector to do it. And the collision rate for dark matter is fairly low. So you need a large volume detector, and you need an experiment running for a long time. So these experiments involve tons of detector material, and they have to run for 5 or 10 years to have a meaningful result.
All right, the next question is from Remiscript, who's on with us live. Hello, Professor. My question is, after the process of Hawking radiation emits, being emitted, does the energy that's emitted contain any traces of the object which was previously consumed by the black hole?
No. So Hawking radiation is radiation, and as with photons in general, so just a form of radiation or photons, and photons have no specifics about their origin, the nature of their origin. And so radiation is essentially mute to the interior nature of the object from which the radiation came.
The next question is from No Name. In a presentation that this person saw, they presented a view that a telescope located on the dark side of the moon may be useful for cosmological observations. Do you have any opinions on the idea of placing a telescope on the moon?
Sure. I mean, astronomers have been contemplating lunar-based telescopes for probably half a century. I'm certainly aware of NASA studies of lunar-based telescopes that go back to the 1980s, so design studies. The dark side of the moon is a completely pristine environment for building a telescope of any kind. For an optical telescope, obviously it's extremely dark. There's no atmosphere, so it's as good essentially as being in space. But you have a stable substrate, a geologically quiet foundation on which to build a very large object, presumably using robots to construct it. And similarly to optical and infrared, radio astronomy is extremely well done on the moon because it's a perfectly radio quiet environment, and the moon would be shielding whatever ambient radio communication might be leaking away from the Earth. So there are no current ongoing plans for a lunar base or if there were a lunar base, I suspect astronomy would eventually be part of it. But as a standalone robotically constructed project, there's no current lunar observatory underway, and the costs, of course, would be quite substantial.
The next question is from Miles, who sent an email. Is the process of star formation uniform across the universe, or are there any interesting anomalies to this process?
Star formation does very much depend on local conditions. So in galaxies that have star formation, like spiral galaxies, like the Milky Way itself, the process and efficiency and yield of star formation varies very much on local density in the environment. And we can see examples of this really nearby in the Milky Way, because we have the Orion arm of the Milky Way, and we have the Orion star-forming region, which is an extremely massive molecular cloud that's forming hundreds of massive young stars. So that's a large amount of gas being fairly efficiently converted into massive stars. If you go to an interarm region, a region between the spiral arms of the Milky Way, which we can also study nearby, then the efficiency of star formation goes way down. So just in a single galaxy, you can have star formation efficiencies from the raw material of the gas that vary by orders of magnitude. And then, of course, there are some galaxies like ellipticals, giant ellipticals, that have very low gas content, and so their rate of star formation is extremely low over all cosmic time.
The next question is from Saad, who's on with us live. In spiral galaxies, since all stars follow circular paths around the core of the galaxy, why does the distribution of stars appear as spiral arms connected to the core of the galaxy?
So that's a good question. So the existence of spiral arms and the pattern of spiral arms was first understood probably about half a century ago, maybe in the 1960s. And the spiral pattern is essentially a pattern. It's not a fixed situation where the density of stars is higher in the place that outlines the spiral arms. The stars are indeed all moving on circular paths, and those stars move in and out of denser regions on their circular paths. And in those denser regions, there's more likelihood of collapsing a gas cloud to form new stars, and so you see stars forming there. And then those stars will continue to move in their circular path out of the denser region, and so the region will fade in its surface brightness. And so what we see as a spiral pattern is not a fixed part of a galaxy, just rotating with the galaxy. It's a pattern where the stars that are part of it move in and out of the pattern on their circular orbits.
Excellent. The next question is from Hassan, who is on with us live, who asks, how do you think we in the Middle East could begin to update and advance our knowledge in astronomy, and in what ways could this development benefit our societies?
Well, in the Middle East is a place with a long and rich astronomy tradition, of course, going back thousands of years. There were certainly times in the last 2,000 years when European astronomy was not really developing very well at all, the Dark Ages, the Middle Ages, even up to the edge of the Renaissance. And innovations and observations were happening in the Arab world and in the Middle East. So there's a long tradition to build on there. As for the future, the Middle East does have, of course, a good intellectual tradition and very big major universities that could be the basis of strong astronomy departments. In terms of facilities, it's probably best if the countries in the Middle East collaborate on facilities, because by pooling their resources, they're more likely to build better facilities. There are some good observing sites in the Middle East. Egypt has some high mountains. Obviously, Turkey has high mountains in the Atlas region, and Morocco, and so on. So slightly broader than the Middle East, you have some high observatory sites. Radio astronomy could be done well in the Middle East. So I think there are definitely opportunities for cutting-edge astronomy to be done in the Middle East, but it requires the health of their universities, since, again, astronomy is not a core discipline that's going to lead to economic growth or generate many jobs for those societies. So it will require a major university to have an intellectual base to support the astronomy activity.
Thank you very much. The next question is from David Gold, who is on with us live. What organizational or cultural challenges have there been or have been overcome between organizations like NASA, the University of Arizona, Lockheed Martin, to construct things like the James Webb Space Telescope, the NIRCam, and make sure that those are successful?
So major astronomy, especially for space telescopes, is a highly collaborative arrangement. Most universities simply do not have the technical resources or capabilities to build an entire space project, or even necessarily an entire space instrument for a space telescope. And so it's typically a collaboration between a university and a major aerospace vendor that can deal with the detector arrays that are often involving classified technologies, and high quality optics. And so this collaborative arrangement has been in place for quite a long time, for decades. All the Hubble Space Telescope instruments involve collaborations between universities and companies like Lockheed Martin and Raytheon and so on. So this is a strong tradition in astronomy, and it's due to the expense and complexity of building a space instrument that you actually need to often be working with a company that deals with space imaging or space telescopes or satellites as part of their business, because universities are not always doing this routinely. And that's why these collaborations tend to be successful. They're not perfect because the interface between the university and the corporation world is not always perfect. There are inefficiencies. There's quite high overheads because the overhead rate charged by some companies is much higher than the university overhead rate, which is typically 50 or 55%. In the corporate world, that overhead rate can go over 100%. So the cost of these projects is substantial.
The next question is from John, who's on with us live. If I recall, there's a six-planet planetary alignment going on in the sky right now. Do you know how long this is going to last and where it's visible on Earth?
I've not been keeping up with the sky maps recently. I haven't been on a trip. I was immune from the sky because we were under mostly cloudy skies in the North Atlantic. So I'm not really well placed to answer that question right now.
Okay, I did look it up real quickly, and it seems like it started early August, and it's kind of ending right about now because Mercury's getting too close to the horizon. So that's, I mean, that debate briefly, that's what I found online from a quick search. Um, so the next question, we'll move on to Zelda. I'm a pharmacy student. Do you think it's possible to transition to a field like astrobiology from this kind of background? Do you think, are there any intersections between pharmacy and astrobiology?
There can be. If you're a pharmacy or pre-med, then you obviously have done foundational biology classes. Certainly, if you've done molecular or cell biology, or maybe even developmental biology, that has a strong play into an astrobiology degree. However, astrobiology also, the astro part of astrobiology is important. So from a pharmacy background, you would need to augment your education with physics, math, and astronomy courses to round out what an astrobiologist's skill set would need to be.
The next question is from Arif Roni, who asks, how do scientists become principal investigators, and what are their roles other than just being, an astrophysicist on the team?
Right. So the phrase principal investigator has kind of a specific meaning in the world of projects and grants and contracts. A principal investigator is someone identified by a project, and this is typically a federally funded project by NASA or the National Science Foundation, who has overall responsibility for the project. They have fiducial responsibility for the performance of the project, for the accounting for the grant that's delivered to do the work, for reporting on the project and reporting out the grant, for overseeing the nature of the expenses and that all the expenses are appropriate, for hiring the personnel to do the work and monitoring their activities. So it's quite an onerous almost set of responsibilities for a principal investigator, especially on a multi-million-dollar project. But even for a small project, the principal investigator is the single point of contact with the granting agency. So if you have a grant of any size from the National Science Foundation or NASA, then the program officer or the administrative part of the agency will always be dealing primarily and fundamentally with the principal investigator to get their questions answered.
The next question is from Ernest, who asks, what is a black moon? And have you heard that term before? And what does that describe?
Black moon?
Yeah, that's what it says on here.
Okay,
Are you familiar with that?
I'm going to pass. Haven't heard of
Okay.
that.
So then the next question is, what is a space elevator? And is it possible that something like that could be created in the foreseeable future?
So a space elevator is an idea that goes back a long time, over half a century. Arthur C. Clarke, famous science fiction writer, but also a space visionary with very strong technical training, he talked about space elevators, I think, even in the 1950s. And when he was asked when we would have a space elevator, he said 50 years after everyone stops laughing. Well, people have pretty much stopped laughing now. So a space elevator is essentially a cable held up against its own gravity by a centrifugal force of the spinning Earth. And that means it actually has to project very high above the Earth, far above geocentric orbit, to about 250,000 miles away, almost to the distance of the Moon. And then it has to be suspended against its own weight. And so the requirement, of course, is of a material of an incredibly high tensile strength to not break under its own weight. And if you do the math for an elevator or space elevator on the Earth, we know we do not have materials of sufficient lightness and tensile strength to build a space elevator. The best carbon nanotubes, not really good enough, but they're not missing by a large factor. However, a elevator on the Moon, a lunar elevator, is close to being a real possibility. The advantage of a space elevator, if you can build one and then stabilize it, and that's a big deal because such a long cable is subject to various instabilities and oscillations, so stabilizing it is not trivial. You have the elevator, and then you essentially put solar-powered lifters, cars moving up and down, sliding up and down the cable, carrying a payload. And because they're solar-powered and because the cable takes you to a point of zero gravity and orbital velocity, you've essentially removed the need for rocket fuel. So you've made getting to Earth orbit essentially free. So it's an incredibly ambitious and great goal if you can achieve it. As for how far away are we from a space elevator on the Earth, it's maybe not 50 years, but it's some amount like 20 or 30 years. However, the cost of the project, if the technical challenges can be met, is not extraordinary. Various studies have suggested a cost of $10 to $15 billion, which is not out of hand with other big space projects.
The next question is from Terrence, who asks, we'll go through, there are three questions. We'll just go through them in order. First is, can you explain the solar cycle?
Yeah, the solar cycle is a 22-year cycle where the sun's reversal of its magnetic field, and the sun generates its own magnetic field from nothing by the dynamo effect, which is a differential rotation. So a small seed magnetic field is gradually amplified and then built up into a full magnetic field, and then the differential rotation of the sun gradually twists those magnetic field lines until eventually they scramble and reconnect and that field disappears, and then the cycle repeats. And the telltale of the solar cycle are sunspots, because sunspots represent the places where magnetic field lines go in and out of the photosphere, and therefore in pairs you see slightly cooler regions, and so you have pairs of sunspots where those magnetic field lines penetrate the photosphere. And when the magnetic field of the sun is at a maximum, there will be many sunspots, and when it's at a minimum near the field reversal time, the sunspots numbers will go down to essentially zero.
The next question is from one of our live participants who asks, how does something like zodiacal dust may affect astronomical observations? And is it a potential complexity, or does it make it difficult to detect things like exoplanets, and how do astronomers plan around or get rid of signals like that?
Yeah, the zodiacal light is very low level emission from tiny microscopic dust particles that are sitting in the plane of the solar system. And so these are just tiny bits of debris essentially that never got swept up into making planets or moons, but they occupy the solar system. And so in the ecliptic, which is the plane of the solar system on the sky, and varying out in angle from the ecliptic by 5 or 10 degrees, you'll see a very dim band of emission from these tiny dust particles. So it's essentially a sky glow. And as a sky glow, it does interfere with deep astronomical observations. So when you're looking in the direction of the zodiacal light, the limiting magnitude you can see and the depth you can see is substantially less than when you're looking out of the plane of the solar system. There's no way to go get around this except by not looking in along the ecliptic.
The next question is from one of our live participants. I'm not familiar with this. I don't know that this is accurate. So if not, then we can just move on. But they say that apparently hundreds of stars seem to have simply disappeared when comparing old photographs from before 1950s with recent photographs. Are you familiar with this? Could this be caused by errors in photographs? Is this something that, you know, astronomers are aware of or dealing with?
Yeah, I can't comment on this, so I haven't seen the story. I mean, when you're comparing historical images of the sky with current images of the sky, it's a little tricky because, um, especially in the historical era of photographs, it's hard to tell what the depth of a photograph is. And the photographs, of course, have various backgrounds and photographic fog and so on. So these are not perfect imaging devices. So it makes comparisons a little tricky. You muted?
Sorry about that. I thought I clicked the button. The next question is from one of our live participants. Is there a competition among world superpowers to be the first country to detect an alien signal? China has now got the largest ground-based radio telescopes. Is there any competition for this to happen?
I suppose in principle there could be competition between the world powers to detect the first alien civilization. I mean, because if you view extraterrestrial civilizations as extension of terrestrial power or part of a larger community of world powers on a larger stage, then you would want to be the first to put forward your proposal to be the Earth's representative superpower, maybe China instead of the United States. But in practice, I don't think there's a real competition because the odds of detecting extraterrestrial civilizations are so low. The Chinese do indeed have the largest radio telescope, 500 meters, and it's doing excellent radio astronomy as well as searching for artificial signals from civilizations. But this is not a type of science where you can estimate your odds of success. So it's not really a realistic competition in that sense.
The next question is from Terrence, who's on with us live. I have a question about the microwave background. So when we look at these pictures that look kind of like heat maps of the sky, the red and yellow colors, what does that represent? Does it represent like stellar plasma? Like what do the colors that we're looking at in these cosmic microwave background images represent?
So the first thing to realize when you're looking at an image of the microwave background is you're looking at false color because these are microwaves. Microwaves are invisible to the eye. They're very long wavelength radiation that the eye can't detect. So essentially you have to take those wavelengths and upscale them or take them up in energy to an optical range to apply a color to them. But if you do that by some fixed factor, then they do represent hotter and colder areas, except they represent microwaves, higher and lower intensities of microwaves. And typically the way the color coding works is that the bluer regions represent cooler or a lower intensity of microwaves, and the redder regions represent hotter or higher intensity of microwaves in the microwave background. And because the microwave background radiation is almost completely uniform, very, very similar temperature to a small fraction of degree, these fluctuations, the difference between the bluest blue and the reddest red in these maps is very small. It's typically on a microwave radiation of 2.7 Kelvin, it's typically a thousandth of a Kelvin between the bluest blue and the reddest red. So the radiation is essentially very uniform and almost a perfect single temperature.
The next question is from Georgia, who's on with us live, who asks, does the event horizon of a black hole completely surround the black hole?
Yes, the event horizon is a sphere for a black hole. It will be an oblate sphere for a spinning black hole, so not in other words, not perfectly spherically symmetric, but it is it's indeed a spherical region, excising that part of space-time from the rest of the universe.
Um, can you talk a little bit about why the descriptions or the depictions we see of black holes often make them seem like they have these disks or the sort of a two-dimensional kind of view of it, and how does that differ from what we sort of know of or what you described just now as like a three-dimensional, horizon?
The black holes, the images, the artist's representations of black holes, because we only really have a handful of pictures of real black holes taken by the Event Horizon Telescope, and they're big ones. Um, the black holes that you see in those images, artist representations, are representing the accretion disk around the black hole. So when there's a deviation from a single spherical dark object, it's typically because they're representing the equatorial region of the spinning black hole, a hot disk of very hot gas, plasma, millions of degrees Kelvin, that glows and emits X-rays. But of course, you can't see those, so they make a visible representation. And this material is swirling around the black hole, and at the inner radii of the accretion disk, it is indeed falling onto the black hole and slowly increasing its mass. And that's typically what these visual images are showing.
Thank you. The next question is from Lawrence, who's on with us live, and asks, regarding the expansion of the universe, is the universe expanding into existing space, or is the universe creating new space?
I think it's the latter. So the universe is not expanding into anything. So the understanding of the expanding universe in general relativity is that space-time itself is expanding and not into any external medium. The theory does not require an external medium. And so we don't invoke one, and we imagine the space-time is expanding itself. And so indeed, new space is being created by this expansion. And we think that space is being created at an accelerating rate due to the effect of dark energy.
The next question is from Hernan Reyes, who sent an email. There was an offshoot of SETI called Serendip 5, the fifth version of the search for extraterrestrial radio emissions. It was sort of built around the Arecibo radio telescope, but since Arecibo is no longer in existence, do you know anything about the status of this Serendip 5 project? Is it morphed? Is it still around? How does it work now?
Yeah, the Serendip project, number 5, it finished over a decade ago. I think there was a Serendip 6, but it also has been over for a long time. The Serendip series of projects were essentially what you call piggyback radio surveys. They were designed to use an existing radio telescope, Arecibo dish or others, and that was doing regular radio astronomy, and essentially piggyback it by getting the data and looking for signals from extraterrestrial civilizations. So it's essentially leveraging existing radio observations with a piggyback survey to look for SETI signals. And that was a very successful, it was successful, not that real signals were found, but it was a very effective technique. And that essentially has been over for a while. Arecibo, of course, crashed spectacularly some years ago. There are now some successive telescopes. There are now some projects doing SETI with, citizen science sort of methods. There was SETI at home, and that sort of stopped also about a decade ago. And I think the current suite of SETI projects that citizen scientists can get involved in using their phones, for example, and an app, are in the BOINC app, which is a suite of applications in an app that all relate to various SETI projects. And you can do this essentially use the power of your smartphone to help with these surveys.
The next question is from one of our live participants. In your opinion, what is the most promising place in our solar system to look for microbial life? Europa, Enceladus, Mars. Is there another one that might be better?
I mean, if we had the tools to investigate the correct region, I think subsurface Mars is at the right mid latitudes is still the best place to look. We know there are places on Mars that were wetter and warmer in the past. That's very ample evidence of that. We also know that the conditions are such that there could be liquid water in subsurface aquifers on various places on Mars. And so, if we could identify a place where there was a subsurface aquifer using radar techniques, perhaps, which we don't have the ability to do right now, but we might in the future, um, we would identify that region. We might have to drill tens or hundreds of meters to get to the aquifer, but that's a place where microbial life could exist even now. And given that Mars is substantially closer than those outer solar system targets for microbial life, such as Enceladus or Europa or possibly Titan, Mars is still the best place to look.
The next question is from one of our live participants. Um, and they would like to know if you can sort of talk about is it is astrobiology um, is it fair to compare astrobiology to string theory? So, for example, because it's so difficult to see exoplanets, is that as the idea of searching for life on these exoplanets sort of just as far-fetched as the sort of speculative ideas in string theory?
I don't think it's a fair comparison for this simple reason. The astrobiology techniques are indeed they're very difficult when it comes to identifying microbial life, but the techniques are well understood and they're well developed, and the methodology of the search is well understood, and the experimental basis for doing it with larger telescopes and new space instruments is on the horizon. So I think we're approaching very powerful astrobiology experiments to detect life. String theory is in a different category because string theory is predicated on a foundational change in the way we think of matter to be tiny one-dimensional strings that operate in an energy scale that's many dozens of orders of magnitude higher than any energy we have access to. So the enormous gulf between the highest energy we can reach in the lab or with an accelerator and the string theory energy regime makes that an enormous reach and highly speculative. Whereas astrobiology, there's a research program underway and a real prospect of success in the next 5 to 10 years.
The next question is from Anjali. I'm going to try and interpret what I think I understand. The question is, how is a breathing air, oxygen, made aboard spacecraft? Do they make the oxygen in space? Do they just carry oxygen with them? I mean, how does that process work?
And that's a good question. So in something like the space shuttle or a sort of short duration space mission, you essentially don't need to worry about oxygen. There's breathable oxygen. Gradually, of course, it will be metabolized and the carbon dioxide content will increase. But with pressurized oxygen that you bring with you, you can easily stabilize the oxygen concentration. In longer duration facilities like the space station, where there's continuous human habitation that's been there for decades now, you have to have more additional sources of oxygen. So essentially, you have to scrub the atmosphere and recycle it. You still have to deal with the fact that given humans and respiration, you're going to deal with a gradually increasing carbon dioxide content. And so the keeping a breathable, healthy atmosphere involves scrubbing the carbon dioxide out of that atmosphere. When humans go to different environments and set up bases, such as on Mars or the Moon, then you have a much different problem. You have to create the oxygen because you can't bring it with you. It's too expensive, too difficult. And there, the oxygen will be extracted from oxides in the rocks by hydrolysis, by electrochemical methods. And so it is fairly well understood, with not too impressive or complicated technology, how you can extract oxygen from the soil on the moon or Mars that you would then use to breathe.
Excellent. Thank you very much. The time is now 10:59, so we're going to take one more question and then we will wrap up for today. The last question is from one of our live participants. Is there any alternative to using glass in telescopes? Is there, could we use polymers or plastics for these optics, to make telescopes that are lighter or larger, or for space telescopes? Are there any alternatives to these reflecting surfaces or lenses?
Yes, there are alternatives. Glass is the cheapest material, and typically in our mirrors, for example, here, and in most big mirrors, it's borosilicate is the actual material you're using, but it's essentially glass. It's the best material for large ground-based telescopes. But when you go into space where weight is a premium, then there are other technologies. The one that's been used in the past and is going to be used in the future is to make a telescope out of beryllium. Beryllium, obviously one of the lightest elements, so is essentially the lightest possible way you can make a mirror. And it is intrinsically highly reflective and non-corrosive. So beryllium mirrors are a good way to go in space. The downside is they're quite fragile and brittle, and the space environment can be rather unforgiving. So in space, beryllium is an option, and it does have enormous advantages in weight, but it's tricky to work with. Well, thanks for your questions today, covering a lot of subjects as usual, and we'll get together, Matthew and I will get together and figure out the next timing of the next few sessions. Thank you.
Excellent. Yeah, thank you all for joining us. We do not have the next one scheduled. We usually have these about every 2 weeks, so keep an eye out for that. If you have enjoyed our session, hit that thumbs up button and subscribe to our YouTube channel, and click the bell icon, and that way when we announce the next session, you'll hear about it. But again, look for that to come out in about 2 weeks. So take care, everyone. We hope you have a good weekend and enjoy. The September is right around the corner, so we hope you have a good rest of your month, which is very short. All right, take care, everyone.